In this video we discuss some common type of signals and systems for communications. These signals will be used in the later videos. So what is basically a signal? It's simply a set of information or data. For example, we can have a telephone or a television signals. So it's generally plotted against an independent variable, which is the time. So on the x-axis we have the time, and on the y-axis we have the variations of the signal. So the signal could be the our voice, for example, that changes with respect to time. A system is anything that any process that has an input signal and it gives us an output signal after processing the input. Can be it's called a system. So for example, a circuit that has a capacitor can also be called a system. We can have a microphone. What it does is it converts the sound input to an electrical output, so that's also an example of a system. We can have a larger system as well. So for example, a communication system, which is composed of subsystems such as transmitter, channel, and receiver. So how is generally a system represented? So we have an input which is generally denoted as xt. It passes through the system and we get an output yt. The time t stands for the time variation, so the independent variable is time in this case. In a very broad sense, we can say that the output signal, the system here can be represented as the output divided by the input, so the ratio of these two quantities. So or that means if we multiply the input with the system, we will get the output yt. So common measure, so there are situations where we have to measure the size of a signal. So just to know if one signal is greater in energy or power than the other signal. So there are two different methods of doing that. So first is energy signal, or size of a signal is determined by determining the energy of the signal. Energy, if we denote it by EGT, this can be determined for real signals. We can determine it by g square t, integral from minus infinity to plus infinity. So to set a standard, we measure the strength. To set a standard for signal strength measurement, the signal Gt is generally considered as a voltage across a 1 ohm resistance. So as you know, in the formula for power and energy, we have the contribution of resistance as well. So as a standard, we keep that equal to 1, and so that's why it does not appear, for example, in this formula for energy of a real signal, or in this formula, which is energy of a complex valued signal. So for complex valued signal, we consider the modulus of the signal. Why does a square appear here? Because for example, a sinusoidal wave or other different type of signals can have a positive and a negative cycle. The negative cycle does not mean that there is no, it's we are, some sort of subtraction is going on from the energy. So in order to avoid that, we take the square of the signal, so that the integral gives us the actual energy, and the negative cycles do not subtract from the positive part of the signal. So there are some signals for which the energy does not exist. We cannot find it. So for example, we have a sine wave. So if we try to find out the energy of this signal by using the previous formula, we will get an infinite value. So a necessary condition for energy to be finite is that the signal amplitude goes to 0 as time t approaches to infinity. So in this case, for example, in the case of a sine wave, this is not true. So in those situations, a more meaningful measure is the time average of the energy. And it may not always exist, so we have to define the signal accordingly. Now, time average, if we denote power as G is the signal, then we have the limit time t approaches to infinity, means for a very large time period we determine the power by using this relation. So if you look at the limits, this is for one time period t, from minus t by 2 to t by 2. So whatever is the limit here, the difference between these two must appear in the denominator over here. For this is for real signals. If we have a complex signal, then we take the modulus square of that signal to determine the power of the signal. So the signal power, as you can see here, is the time average or mean of the signal amplitude square. So that is, we can also call it mean square value of GT. And this is related to the root mean square that we are quite familiar with, the RMS value of signals. So that means the square root of PG, this signal, will give us the RMS value of GT, right? So this is how it's related to, the power is related to the RMS value. So we can, for example, in this case, this signal will have finite energy, so we can call it an energy signal. In this case, the signal will not have a finite energy because it's not going to zero with time. So we need to consider power for this. We need to consider the time average of energy, which will give us a finite value of power for this signal. So then there are third type of signals where the signal does not have a statistical regularity. There is no time period after which the signal repeats itself. So for example, if we look at this signal, the ramp signal, or an exponential increase, these signals do not have any energy. I mean, these signals, we cannot measure their energy, and we cannot even measure their power, because they will give us infinite values for energy and power. So these are the signals for which we cannot determine these two quantities. So based on this, we can actually define the signals. So for example, the signals for which energy exists, we call them energy signals. For signals for which power exists, we call them power signals, and for signals for which neither of them exist, we cannot call them any of the two categories. So what are the units? Generally, we can have the unit as joules and watt. Joule is for energy and watt is for the power. But commonly we use logarithmic scales. So the energy is defined in decibels. In this case, we have dB watt, dBW. That means if when we determine log 10, 10 log 10 of P, power is the linear value P. The denominator here is in watts, so it's 1 watt. The reference here is watt, so that's why the resulting unit would be dB watt. So if we measure this in dBm, so in that case we will have the same formula. The only change would be the reference here in the denominator would be 1 milliwatt. So we will have 0.001 watt in the denominator, and so this is how these two are related. So we will have dB watt, and we have dBm. These are the two different units. It's just that the reference for their measurement, for finding the unit, is different for these two. And they are related. If we want to find out value, we want to convert a value from dB watt to dBm, we have to just add 30 to that value, and the new value we will get would be dBm. So Then we have classification, or we discuss the classification of signals here. So we have continuous time signal. The classification here is basically based upon the two axes. So we have the time axis and we have the y-axis, the amplitude axis. So continuous time signal are determined by the time axis. So if the time axis is it has infinite values in the this is called a continuous time signal. So what do we mean by infinite values? So for example, between these 2 points we can have infinite values. So we can have 1.1, for example, the next value can be 1.01 and 1.001 and so on. So we will have infinite values between any 2 points, and such type of signals are called continuous time signals. Then we have the discrete time signals. Again, the continuous and discrete is determined by the x-axis, the time axis. So in this case, the points can take on only discrete values. So it can be like integer values 0, 1, 2, 3, -1, -2, and so on. Right. So then these were the two signal types based upon the time axis. Then we have further signal types that are based upon the amplitude, the y-axis. So if we have infinite number of points on the y-axis, then the signal is called an analog signal. If we have finite number of levels on the y-axis, then that signal is called a digital signal. So this discussion is summarized in this slide. We can see the first type A is an from the it's an analog signal because of the y-axis, and it's continuous time because of the x-axis. This B is a digital signal because the number of levels are fixed. There are certain set of levels. In this case, there are only 2 levels, and but the y-axis, x-axis is continuous, so it's called a digital continuous time signal. This one is a digital. Sorry, this one is an analog uh, discrete time signal, because on the y-axis the values can take we can have any value. On the x-axis we can only have discrete values, so this is an analog discrete time signal. And finally, on the y-axis we have two set of values only, and on the x-axis also we can only have some discrete values, so this is called a digital discrete time signal. Then we have periodic signals and aperiodic signals. So for periodic signal, this equation is valid if a signal has this equation. If it's valid, then that signal is called periodic. So T naught is a time after which the signal amplitude repeats itself, and aperiodic is a signal that does not repeat after any time t. So this is the information based on classification based on periodicity. Then we have classification based upon energy and power. So for example, if this equation is valid, the energy of a signal is finite, then we call that signal as energy signal. If the power is finite, then we call that signal as power signal. Power should be greater than 0 and less than infinity. So in that case, the power of this signal is so in that case, this signal is called a power signal. Right. So an important point is power is the time average of energy. So averaging is over an infinitely large interval. If you see, this is a very large interval. So if a signal has finite energy, and if it's divided by such a large value of time, then the power in that case would be 0. So that means an energy signal cannot have any power. It will not give us any meaningful value for power. So a signal will either have an energy or it will have a power. So that's an important point. It cannot be both an energy or a power signal. So then we have the deterministic and random signals. Random signals are the ones that are purely random. They naturally exist. For example, noise signals are random. And we have situations where we want to like simulate the noise in our system. So in that case, we define an expression, and we try to simulate noise and try to make it as random as possible. But again, in order to do that, we have to define an equation, an expression that the system follows to generate the noise. So in that case, the noise is deterministic. Or in other words, it can be called pseudo-random. So it cannot be just completely random like the natural noise signals we have. Then we have the unit impulse signal. So unit impulse is we have an infinite impulse at time t is equal to 0. It can be at any other time as well. So this delta t is 0 at any other time apart from 0. And this is the example of an ideal unit impulse, but practically we have impulses like these where the width of the signal is very narrow, and the height is the reciprocal of the width, because by definition the unit impulse, the area under unit impulse is equal to 1. So in order to keep that area equal to 1, even in the practical impulses that we have here, the width and the height are reciprocal of each other. So if we multiply them to find out the area, or we take the integral of this, so this will again give us a 1. From unit impulse, it has an important property, it's called sampling property. So if we multiply a unit impulse with a signal, so we will get the value of that signal at the particular time where the unit impulse exists. So this unit impulse will exist at time capital T. There will be an impulse over at this point T. So when we multiply this with the signal, the value that we get is the value of the signal at that particular time T. So this is called the shifting or the sampling property of unit impulse. Then we have a unit step. Unit step is so ut, it has a value of 1. There's a sudden or discontinuity at point at t is equal to 0, and the value goes to 1, and then it's like it stays 1 for the rest of the time. So it's a right-sided signal, and so we can call it a causal signal as well. Another example of causal signal is this exponential signal, which is a right-sided signal, so it's causal. Now we observe that the area from, so the relation between delta t and ut can be observed from this expression. So if we take this integral from minus infinity to t, this will have a value of 0 until t is less than 0. When the t is greater than 0, this integral will give us a value of 1. So if we look at this formula or these expressions, they are the exact representation of ut. So this is how delta t and ut are related. Similarly, from this we can also say that the derivative of ut gives us delta t because of a discontinuity at this point. When we take the derivative, we will get an impulse at this point. So in summary, we have studied what the signals and systems are. How do we measure the size of the signal? We have continuous and discrete signals, analog and digital signals, periodic, aperiodic, energy and power signals, deterministic and random, and finally unit impulse and unit step signals.